Hey students, good morning. So in this session, we are going to discuss about initial value theorem and final value theorem, which belongs to Laplace transforms. Okay, so the last session we discussed the problems which are belongs to the Z transform. Okay, so now we are going to discuss about the Laplace transform. Okay, so already we know the definition for Laplace transform and the notations of all the notations of Laplace transform. Okay. So once again, I want to recall the notation and the definition of Laplace transform. Then we will discuss about the initial and the final value theorem. Okay. So first look at the definition for Laplace transform. Okay. So f of t is a given function. Okay, and the Laplace transform of the given function f of t is equal to integral 0 to infinity e power minus st into f of t into dt, where s is greater than 0. Okay, and this expression, after finding the Laplace transform, we will get one function which contain the variable s. Okay, so therefore the resultant of this expression will be the function of s. So we can give the notation for this function or the Laplace transform is f of s. Okay, so um, so this expression, this Laplace transform of f of t will be equal to some function of s only. Okay, so already we have discussed these things, but anyway, I want to recall these things again. Okay, okay. So next thing is uh, we know that Laplace transform of f dash of t. Okay, the derivative, the transform of this derivative. So this is equal to s times Laplace transform of f of t, okay, minus f of 0. Okay, so this is another formula. Okay, so that means transform of the derivative. Okay, again, if you simplify this with this notation, this can be written as s into the function of s minus f of 0. Okay, because already we know that Laplace transform of f of t is this f of s. Okay, so therefore this expression, that means the Laplace transform of f dash of t is written as s into f of s minus f of 0. Okay, so this one is the first one and this one is the second one. Okay, now we are going to discuss about the definition of initial value theorem as well as final value theorem. Okay, so in which we will use this expression. So that's why first we have recalling this expression. Okay, then we will give or we will discuss the initial and the final value theorem. Okay, so first to write down the uh, final value theorem. Okay, or initial value. First we will initial value theorem. Okay, so this is initial value theorem. Okay, so here, um, if Laplace transform of f of t is equal to the function of s, already we know these things. Okay, so then this statement is always true. Limit t tends to 0, f of 0, sorry, f of t. Okay, so this is f of t will be equal to limit s tends to infinity s into f of s. Okay, so this capital F of s is nothing but Laplace transform of this f of t only. Okay, so this is the statement of initial value theorem. Okay, so first we will discuss the proof of this theorem. Then we will discuss problems based on this theorem. Okay, so first look at the proof. Okay, to prove this theorem, I am going to use the result 2. Okay, already you know this result. Okay, so already we know that okay, so the Laplace transform of f dash of t is equal to s times function of s minus f of 0. Okay, now you just look at this expression here. um, For this function s into f of s, we are taking the limit s tends to infinity. Okay, so therefore, first you take limit s tends to infinity on both sides for this expression. Okay, if you use that, then take limit s tends to infinity on both the sides. Okay, then this expression becomes limit s tends to infinity. Okay, Laplace transform of f dash of t, okay, is equal to limit s tends to infinity s into f of s minus f of 0. Okay, so this is the resultant expression. Okay, so now I continue this problem here. Okay, so now you expand this one. Okay, so already we know that Laplace transform of f dash of t. You just use the original definition for Laplace transform. So here we can write that 0 to infinity e power minus st into in the place of f of t we have f dash. Okay, so therefore this can be written as f dash of t into dt. Okay, so this is the definition of Laplace transform. Okay, and in the right hand side is just to keep this expression as it is. So s into f of s minus f of 0. Okay, okay. So now here we are approaching this s tends to infinity. So therefore this the variable s is involving only in this expression e power minus st. Therefore, if you approach this s tends to infinity, this becomes e power minus infinity. E power minus infinity is 0. So therefore, this value of this expression will be equal to 0. Okay, so 0 is equal to limit s tends to infinity and s into f of s minus f of 0. Okay, here 0 because e power minus infinity equal to 0. Okay, so this is minus e power minus infinity is 0. So therefore, this left hand side value will be equal to 0. Okay, and here you look at this expression. In this expression, we are taking the limits or we are approaching this limit infinity for this variable s only. Okay, but in this expression s is involving only in this first term. Okay, so there is no s variable in the second term, so therefore this can be written as again limit s tends to infinity s into f of s. Okay, and this is some constant term only. Even if you take limit s tends to infinity for this expression, you will get only f of 0. If you bring this f of 0 to left side, this can be written as f of 0 is equal to limit s tends to infinity s into f of s. Okay, and this f of 0 can be written as limit t tends to 0 f of t, isn't it? F of t. Okay, so this is equal to limit s tends to infinity s into f of s. Okay, so this is the proof of this initial value theorem. Okay, so final value theorem means reversely you will get the result. Okay, again, and the statement of the final value theorem will be if Laplace transform of f of t is f of s, then limit t tends to infinity. For the final value theorem, here the limit value is infinity, but in the right hand side the limit value is 0. Okay, so you just look at the definition of or statement of final value theorem. Okay, so final value theorem. Okay. So here, if Laplace transform of f of t is equal to capital F of s, then limit. As I told you earlier, now for the final value theorem, you have to take t tends to infinity. But in the initial value theorem, this will be t tends to 0. Okay, so you just look at this, and f of t is equal to limit s tends to 0. Okay, but in the initial value theorem, here s tends to infinity. Okay, s into f of s. Okay, so the difference of initial and final value theorem will be the limit only. Okay, for the initial value theorem, this is t tends to 0, s tends to infinity. But in the final value theorem, t tends to infinity, s tends to 0. Okay, so this is the difference between final value theorem and initial value theorem. Okay, so the limit only will be changed in that final value theorem. Okay, so now look at this proof. Okay, again I am going to use the result of transform of derivative. Okay, so already we know that Laplace transform of f dash of t is equal to s into f of s, okay, minus f of 0. Okay, now look at this expression. In this expression, the limit is approaching to 0 for this variable s. Okay, so therefore you take limit s tends to 0 on both sides. Okay, so take limit s tends to 0 on both the sides. Okay, so then this expression becomes limit s tends to 0, Laplace transform of f dash of t, okay, is equal to limit s tends to 0, s into f of s. Okay, minus, here there is no s, so of 0. Or first you write like this. Okay, okay, this is s tends to 0. Okay, again you use that definition of Laplace transform, then this expression becomes into 0 to infinity e power minus st into f dash of t into dt. Okay, so this one, and the right hand side, if you split this, then this becomes limit s tends to 0, s into f of s minus limit s tends to 0, f of 0. But here there is no s variable, therefore we can write like this, f of 0 only. Okay, now if you take, sorry, this is 0 only. Okay, if you take s tends to 0, then this becomes 1 only, isn't it? Okay, so this becomes 1 because anything for 0 is 1. So this integration will be e power integral 0 to infinity f dash of t into dt. Okay, because e power 0 is 0. Sorry, 1. Okay, so here if you write this, then limit s tends to 0, s into f of s minus f of 0. Okay, now integrate this, this becomes f of t, and you have to apply this upper and lower limit, then this becomes limit s tends to 0, s into f of s minus f of 0. Okay, next, um, if you apply this, then this becomes f of infinity, but that can be written as limit of t tends to infinity f of t for the first upper limit. For the lower limit, this can be written as f of 0. Okay, so limit s tends to 0, s into f of s minus f of 0. This f of 0, this f of 0 will get cancelled. So at the end, we can get limit t tends to infinity, f of t is equal to limit s tends to 0, s into f of s. Okay, so this is the proof of the final value theorem. Okay. Okay. Now we are going to discuss problems based on this initial and the final value theorem. Okay, so actually problems are very simple. Okay, they will ask that verify the initial and the final value theorem of the given function f of t. Like that only they will ask the question. So you just look at one problem. Okay. Okay. First thing, verify. This is the problem. Okay. The first problem, verify the initial and final value theorem for the function f of t is equal to e power minus 2t cos 3t. Okay. Okay. We look at the solution. Okay. Here the given function is, okay, f of t is equal to e power minus 2t, okay, and cos 3t. Okay. So for the initial value theorem and the final value theorem, in the statement, you just look at that statement. Okay, so in that statement, first write down this statement. Okay, so first one is initial value theorem. Okay, so here initial means limit t tends to 0, f of t is equal to limit s tends to infinity. Okay, s into f of s. Okay, so this is initial value theorem. Okay, so you just look at this expression. Here we need to know this f of s also. F of s is nothing but Laplace transform of this given function f of t. Okay, so therefore first we find the Laplace transform of f of t. Okay, you take this is equation 1. Okay, so in this equation 1 we have this f of s. So f of s is nothing but this Laplace transform of this f of t. So Laplace transform of f of t is equal to e power minus 2t cos 3t. Okay. Okay. Next, here you have to use shifting property because we have the exponential function into some another function. Okay, so already we know that Laplace transform of e power minus at into f of t is equal to Laplace transform of f of t, and you have to replace this s by s plus a. If it is minus, then you have to put s plus. If it is plus, then s minus. This is the first shifting property. So I am going to use this one. Okay. So Laplace transform of cos 3t. Okay. And after finding the Laplace transform, you have to replace s by s plus 2 because here minus 2. Okay. Now, what is our cos 3 Laplace transform of cos 3t? So that will be s by s square plus 9, because already we know that Laplace transform of cos at is equal to, cos means s by s square plus s square. Okay, so this expression becomes s by s square plus 9. Okay, but after finding this Laplace transform, you have to replace this s by s plus 2. So therefore, this resultant expression becomes s plus 2 divided by s plus 2 whole square plus 9. Okay, so this is the f of s. Okay, now you go to this result. Verification means you have to find the left hand side value, and you find the right hand side value and check whether these two values are equal or not. If it is equal, then we have done this. That means we verified that result, initial value theorem. Okay, so that is the meaning. So first I am going to find the left hand side. Okay, so left hand side is equal to limit t tends to 0 f of t. Okay, so that means limit t tends to 0, or f of t is e power minus 2t into cos 3t. Okay, so here if we put t equal to 0, then e power 0 is 1 only, and cos 3 t means cos 0, so cos 0 is 1. So therefore the limit of this function f of t is 1. Okay, now you come to this left side, that means right side. Okay, so right hand side is equal to limit, but here you have to take s tends to infinity, s into f of s. Already you know this f of s. Okay, so limit s tends to infinity, s into what is our f of s? F of s is s plus 2 divided by s plus 2 whole square plus 9. Okay, so here, after simplifying these expressions, you have to take the limit. Okay, so first you simplify this expression, then you take the limit. Okay, so that thing is important. Without simplifying this, if you take the limit, then this will gives us infinity. Okay, so that is also important. Okay, so here I'm going to take limit s tends to infinity. Okay, from the denominator you take s commonly outside. Okay, and in the numerator also I will take s commonly outside. So if you take this, then this becomes s square, and here this will be 1 plus 2 by s, isn't it? Okay, and the numerator I am taking the s commonly outside. Similarly, in the denominator I will take s commonly outside, so therefore that will be s square, because here we have whole square. So s square means 1 plus 2 by s whole square uh, plus 9 by s square, isn't it? Because this s square is common for all these things. Okay, that means I am taking the s commonly from the denominator. Okay, so this expression becomes like this. Okay, so now this s square will get cancelled. Now approach this limit. If you approach this, anything by infinity is 0, so for the numerator 1. Similarly here, anything by infinity is 0, so 1, and this is 0, so therefore 1, so therefore this is value 1. Okay, so here left hand side is equal to right hand side, hence verified the theorem. Okay, hence verified. Okay. So sometimes they will ask the questions from this type of problem. Okay, so you just look at this. Next, we have to verify the final value theorem. Okay, for the same function, because we have to discuss we have to verify both results. That means final value theorem as well as initial value theorem for this given function. Okay, so next one is uh, final value theorem. Okay, okay, so now look at the statement. First write down the statement. Okay, so second, final value theorem. What is this statement? Final value means limit t tends to infinity. f of t is equal to limit s tends to 0. Okay, s into of s. Okay, so this is the statement. Okay, now take the left hand side. Okay, limit t tends to infinity e power minus 2t and cross 3t. Okay, so here if you put t tends to infinity, this becomes 0. So therefore this value becomes 0. Okay, next we find the right hand side. So limit s tends to 0, s into f of s is s plus 2 divided by s plus 2 whole square plus 9. Okay, this one. Now take this limit. Here we have 0 only. If you put 0, then everything becomes 0. So 0. So both are equal. So left hand side is equal to right hand side. So we verified this thing. Okay, so that's okay. Next, I will give the homeworks. You just practice these problems. Okay. So first one is verify this oral homework. Verify initial value theorem and final value theorem for this f of t equal to 1 minus d power minus at. Okay. So that's it. And yeah, so this is enough. Okay. That's it. Okay. Next, one application problem. Okay. Uh, okay. Actually, in the Laplace transform, we have discussed so many integrations with the different limits. For example, the first thing, okay, Laplace transform of f of t. This is basic definition. Here we have this limit integral 0 to infinity e power minus st into f of t into dt. So this is one important result. Okay, with this integration. Second one is Laplace transform of integral 0 to t into f of t. Okay, into dt. So here we are finding the Laplace transform for the integration. Okay, so in this case, this is nothing but Laplace transform of f of t whole, whole divided by s, isn't it? Okay, for the integration we have s in the denominator. For the derivative we have s in the multiplication. Already discussed that result. Okay, for this one. Okay, so already you know this. And one more thing, Laplace transform of uh, f of t divided by t. Okay, so if we have this t multiplication, that we have derivative for the Laplace transform. But here we have the t in the denominator. So in this case, the Laplace transform of this will be literal s to infinity. Okay, Laplace transform of f of t into t. Yes, this is important because the resultant of this expression will be function of s. Then you have to integrate that function of s with respect to s. Then put this limit, you can get the result. Okay, so why I am recalling these things means here we have 0 to infinity, here we have 0 to t, but here we have s to infinity. And one more thing, for the convolution theorem also we have that limit. Okay, so yeah, f of uh, t star f of sorry g of t. Okay, of t and g of t. This, okay, so this is equal to integral 0 to t and f of u g of t minus u into d. Okay, so here we have 0 to t. Okay, so 1, 2, 3, 4. Four type of integration we have discussed so far. Okay, so this is fourth one. Okay, don't get confusion with these limits. Okay, clearly study these four definitions. Okay, so definitely you will use these things to solve the Laplace transform problems. Okay, so now the application means, okay, sometimes they will ask like this: uh, evaluate evaluate into 0 to infinity, okay, e power minus 3t cos t into dt. So this means you just we have to find the value of this integration. Okay. So far we didn't discuss this type of a problem. Okay. So by using, sometimes they will give this statement by using, okay, Laplace transform. Sometimes they may give this statement. Okay. Sometimes they will ask only evaluate this integration like that. Okay. So if you have this type of problem, okay, so immediately you try to use this Laplace transform to find the integrations. Okay, because already you know this definition for Laplace transform of f of t. What is a um, basic definition for Laplace transform? That will be the 0 to infinity e power minus st into f of t into dt. So this is our basic definition. Okay, now you just compare this basic definition with this problem. Okay, in the place of f of t, in the place of f of t, we have this cos t. Okay, so what I want to say here, this integral 0 to infinity e power minus 3t into cos t into dt will be equal to Laplace transform of this cos t. But sorry, this is cos t. Okay, because Laplace transform of cos t is equal to integral 0 to infinity e power minus st into f of t. But in the place of s, we have these three. So after finding this, we have to put s equal to 3. Is this correct? Because if you rewrite this expression, okay, for example, Laplace transform of cos t will be what? 0 to infinity e power minus st into cos t into dt, isn't it? Laplace transform of cos t. This is the basic definition. Okay, but for the given problem, in the place of s, we have 3. Okay, so therefore, you just after finding this Laplace transform, you put s equal to 3, then you can get the original result. Okay, so this is the application problem. Okay, so that means we can find the integration value by using the Laplace transform also, but that integration should contain the limit 0 to infinity. Then only we can use this Laplace transform, because in the Laplace transform only the limit of the integration will be 0 to infinity. So that's why. Okay, so if you have the integration with this limit 0 to infinity, you can use the Laplace transform. Okay, so now what is our Laplace transform of cos t? So s by s square plus 1. But after this, you have to put s equal to 3. We put this 3 by 10. So this is the integration value of this one. So this is another application of Laplace transform. Okay, so already we have this type of integrations with the different limits. So now we have this type of integration, but this is similar to the definition of Laplace transform. Okay, so if we have this integration with this limit 0 to infinity, you can use the Laplace transform to find the integration value. Okay, so this is another problem. So Here you have to choose only the value of s. Okay, once if you identify that s value, then you can find the integration values. That's it. Okay, so with this I stop this session. Okay, so you prepare well for the examination. Now I covered all the topics in your syllabus. Okay, so prepare well for the exam, and at least 10 members should get a S grade from your class. Okay, so I expect that. Let us see. Okay, thank you so much.